Welcome to Episode 3 of Concept Before CAD. I'm Brad Williamson. Now, if you're like me, staying connected to your colleagues often means managing multiple points of contact. Email threads, social media, voicemails. But since I've been using the 3D Experience platform, I've found that my 3D Dashboard app has really improved the way that my team members collaborate about design ideas. For example, Brian recently posted to our design community about his experience last week at the NVIDIA conference in San Jose. It turns out that there's some pretty cool technology that we need for our office. Let's get Brian on the line to tell us more about it.
Hey Brad, pretty cool stuff, right? Especially when you take a giant screen, put on some visualization software from our friends at RTT. Heck, we could replace the whiteboard and our monitors. So what do you think the chances are of us getting one of these?
Well, hold on a second. Even if you could get approval for one of those, I'm pretty sure that the two designs we've come up with so far are not going to handle the weight of a 150-pound display. We better go back to the concept phase, not just design for range of motion this time, but also think about strength and load path.
Okay, I think you're right, man. And I think I could take the 4-bar linkage, maybe turn it on its side to better handle the tension and compression of the bending moment. Can you work me up a model of the giant display? And I'm not sure how it mounts, but maybe come up with an interface bracket, and I'll get to work on a new linkage mounting system.
Well, lots of work to do, Brian. We better get to it.
I'm going to begin this design using 3D primitives. This is functionality that automates 4 things: a sketch and an extrude, but it also takes this extrude here and turns it into its own component that's automatically mated to the primitives before it. So now that I have components, I can mirror them across a top plane, then switch over to my cylindrical primitive, which allows me to rapidly sketch, extrude, and create pin components. And again, the mates are automatic, so the motion's already there. Control drag, use my heads-up mate toolbar to add in a hinge joint, and mating's really easy. For example, if I select 2 pieces of geometry, it tells me what mates might work best here, so I can throw in my hinge. Fast forward a little bit, hey, we're in business altogether. But remember, strength is very important, so we need to run a structural simulation. I'm going to run a structural analysis and run a static analysis on this frame. I'm going to apply 150 pounds in the downward direction, but not just on the face, but remotely. It's going to act at the CG of that monitor. On the back end, where I'm mounting to the wall, I'm going to fixture these faces using a clamp, just basically rigidly restraining it in all directions. I'm going to find contact faces, which allows me to instantly bond my entire assembly together, but if I wanted to, I could apply general contact, which would be a friction no penetration constraint in the entire assembly. Software quickly tells me, hey, everything's connected, you're ready to run. I got the green light telling me that I'm ready to run the simulation and get my results. A few minutes later, we take a look at the deformation. Now this is magnified, of course, but let's get a little bit more quantitative. The actual deformation is about 0.2 of an inch, so it's kind of a lot. And when I switch to the stress plot, we see the high bending stress in those rods. Now this is going to be a little bit probably above the yield of this aluminum material that I'm using. Switch over to factor of safety, and we can indeed see that the bending in these rods, factor of safety is below 1. So a quick fix for this might be to change the material. I'm going to apply a carbon steel and see what the results look like with that material. A little bit lower deformation. Flipping to the stress plot, we're definitely going to be below yield for that higher strength steel. There's some bearing stress concentrations, but overall the rods are pretty good. But these parts might be over-designed. Looking at the linkages, we can use a section plot to really see that the middle isn't carrying much stress because we're just in bending. Okay, let's update the team on the community. I'm going to add in a screenshot, add a few notes, and then I'm going to attach a file. And this is a Word doc that was output from my simulation and automatically contains all my results for my entire team to view.
I need a model of a 70-inch flat panel LCD. Let's see if we can repurpose the one we already have. The measure tool shows this screen is 22 inches. We can use the scale feature to easily resize the entire part. On the community panel, Brian has posted the specs for the touchscreen from the conference. I think we can use direct editing to morph the existing boss into a new mounting bracket that will match the spec sheet. We'll use geometric relationships to flatten these drafted sides, then make the faces flush. Next, I can drag the manipulator robot to rotate the side faces and use the ruler to snap in a precise value. We can add a dimension to control the overall height of the boss, or drag faces to thin out this base plate. Finally, we can stretch out the overall length on both sides. With direct editing, we don't need to know how the boss was created in order to modify it. That's looking great. We're now ready to split the body into two parts. The master model feature builds the assembly structure for us in the single modeling environment. We can isolate the bracket and add a couple of fillets and shell the part to a 1/4 inch thickness. I'll now sketch in the mounting hole pattern on the assembly layout. Mechanical Conceptual instinctively recognizes each sketch vertex as a potential hole location. The Hole Wizard library has all my standard ANSI inch and metric hole sizes, including taps, countersinks, and counterbores. I'll just remove a couple of the unwanted locations by clicking on the points. The holes are automatically added to all the affected components. This should work as a mock-up for the large screen LCD that Brian has his eye on.
Brad, I think we've finally arrived at a feasible design that's actually an offspring of our 4-bar whiteboard mount and our monitor arm, but this one's going to enable us to have the latest and greatest display technology. So you know what it's time for?
Yeah, it's time to go from concept into CAD. We need to take the design from Mechanical Conceptual into SOLIDWORKS so we can finish out the detailed design of all those components. Some of them we'll buy off the shelf, obviously, but there's still a few things we'll need to fabricate. That means production drawings and bills of material.
That's right, and I think a great place to start would be that sheet metal bracket you made for the interface.
I'll save the bracket out of Mechanical Conceptual into the SOLIDWORKS format. Now in SOLIDWORKS 2014, I just open the part. I can use this part in my assemblies and even run a simulation. If I need to modify the underlying design, I can use the FeatureWorks add-in to recognize the features. The M6 mounting hole pattern is recognized as a Hole Wizard feature. We'll edit the holes and change them into slots. No problem. Let's apply the proper material, and since this part was recognized as sheet metal, our flat pattern is automatically calculated.
Okay, we'll have to pause here. That's all the time we have this week, but join us next time when we finish out this detailed design. But before I go, we've had a lot of questions about where you can get your hands on these new tools, the 3D Experience platform and SOLIDWORKS Mechanical Conceptual. Now these are new tools that just went live the first week of April. So contact your reseller for more information or click below and go to our landing page and find out more about SOLIDWORKS Mechanical Conceptual. We'll see you next time on Concept Before CAD.